Good afternoon, everybody. Thank you very much for coming. Let's make a start. So my name is Chris Alexander, and I'm a software engineer for the McLaren Racing Formula 1 team, which means that my job on a day-to-day basis is to build, maintain, and run custom software applications for use by McLaren exclusively within the Formula 1 industry. So today's my first time presenting at NDC, so thank you very much for the warm welcome so far. It would be really helpful to me if you were able to provide feedback, so there are feedback cards on the way out. Alternatively, if you want to drop me an email or send me a tweet with any comments, then that would be really appreciated, and hopefully that will help me improve, ready for what I'd like to be next time. So what I'm going to talk about today is under the heading 0 to 60 in the .NET framework, but it's about how we go about developing software for Formula 1. So I've got some questions for you to begin with, actually, so I have an idea about how much you guys know about Formula 1 already. So who's watched any Formula 1 at all in the past, whether it's just a few bits on TV? Okay, most of the audience, so that's good. Who would class themselves as an F1 fan, someone who follows the sport or a specific team or driver? Okay, a fair few as well. Who knows absolutely nothing about Formula 1? Kind of half a hand. Okay, that's cool. So I don't have to go into a great explanation of what Formula 1 is, but there are a couple of things I'd like to point out which will help kind of frame what I'm going to talk about. So at the end of the day, Formula 1 is a sport, it's a motorsport, and all of the teams and drivers are competing to score as many points as possible on the Sunday afternoon so that they can get as good a position in the championship at the end of the season. And then it's the championship which determines how much prize money you get, which then helps with your budget for the next year, and so you can carry on competing. So at the end of the day, it is a competitive enterprise, and we're all setting out to do the best we possibly can to get the best result on the track and to do as well as we can so that we can carry on racing the next year. Now, Formula 1 is unlike a lot of other sports in that there's an extremely technical aspect to it as well. So maybe, I was thinking about this, maybe sailing is another example, where you've got a combination of that athleticism and competitive spirit and the technical and engineering side of it as well. And I think Formula 1 is probably the most extreme example of a sport where there's a very strong technical and engineering aspect to the competition, because you can take the best driver in the world, and if you put them in a mediocre car, then they're not going to win races compared to an average or half good driver in a really, really fast car. So competing well in Formula 1 is about that kind of competitiveness and that athleticism, but it's also about the engineering side of things and being able to deliver fantastic car components, great analysis, and perform as best you can when it matters on the Sunday afternoon. And it's only those things combined which then gets you great results. So it's an engineering discipline as well as a sport, in summary. Today is going to be a very high-level overview of what we do in terms of software at McLaren. So as it's very engineering-focused, McLaren and Formula 1, it's a very secretive industry in general. We tend not to tell people very much about what we're doing behind the scenes, which is very much a contrast to the kind of the marketing and the big show that you see on the Sunday afternoon. So it's not typically let out to tell you many things. Let's put it that way. So today is going to be very high level, but hopefully it still delivers some really, really useful insights to people who maybe aren't involved in the inner workings of F1 on a day-to-day basis. So hopefully there'll be a lot for you to still find out about today. In terms of specifics of the topics, I'm going to start off by talking a little bit about innovation. Now, innovation isn't necessarily something that's something that we talk about very much in terms of our software, but it's very important to McLaren and its history. So hopefully by talking a bit about some of the innovations that we've introduced to Formula 1 over the years, then you can get a bit of a feel for the history of McLaren and how we've got to where we are today in terms of not just our software engineering, but our engineering in general. Then my next topic area is called big data brackets air quotes. And it's got air quotes for a very specific reason, and I will explain why I think the big data that we deal with at McLaren is different in a very important way to the big data that you might deal with on a day-to-day basis or software engineers in other industries deal with. Next up, I'll talk a little bit about how we as software engineers actually contribute to the show, what we do on race weekends, because we're not just 9 to 5, Monday to Friday engineers. We also work over the weekends on rotation to help the team perform as best they can at the circuit. And so I'll also talk a little bit about how we go about doing that and what our role is throughout the race weekend. And then finally, going into a little bit more technical detail, I'll talk about our software development process and how we've kind of evolved how we build software over the years in order to accommodate the extremely fast-paced and engineering-focused industry of Formula 1. So that's what I'm going to go through. If possible, would it be okay for people to hold questions towards the end? I'll leave plenty of time for questions, so please feel free to jot a note down for anything that you might want to ask, and then ask it at the end. There'll be plenty of time. The other thing I would say about questions is that, as I've mentioned, we're all very secretive in Formula One, so if you do ask something and I kind of stand there and smile and nod politely and decline to answer, or maybe give you an answer that's vague or dodge your question, then please do understand, and it is for competitive reasons that I can't divulge any of that information. So if you do hit on a specific topic area or nerve, and I do dodge that, then please understand then that's the reason why. Okay, so that's all the preamble over and done with, so I think it's probably time that we get started by talking about innovation. And I put this picture up first because, for me, it really typifies McLaren's approach to innovation, and specifically how it permeates throughout the entire business. So this is a picture of what's called the McLaren Technology Campus, which is a series of buildings nestled in the countryside just outside Woking in Surrey, which is where we're all based. On the left, we have the McLaren Technology Centre, which is where racing is based, where we do all of our design work and a lot of our manufacturing. This is also where McLaren Applied Technologies, another McLaren company, is based. And this is where kind of our hub of our operations is for the race team. On the right-hand side there, actually, you've got the McLaren Production Centre, which is where McLaren Automotive hand-build all of their road cars on a production line. So sometimes it's nice to go over there and have a look at what they're doing on a large scale, because they're producing some fantastic cars, which we'll have a very brief look at in a moment. But the reason I wanted to show you this and talk about innovation is because innovation permeates through everything we do at McLaren. So we innovate in our software, which obviously, hopefully you get a good idea about that today, but also in how we're engineering different materials, and in fact how we're building our buildings. So this building was designed by Foster & Partners, the renowned architects, and I found out the other day that the roof is flat because when we were planning the building, we had to build it up to the level of the trees in the surrounding areas. So the building is exactly 11 metres tall all the way across, and it's got a flat roof. But, of course, flat roofs are difficult to drain. And if you're draining a roof that size, then you actually need quite a lot of kind of piping to get the water off the roof. So when they were designing the building, actually all of the outlets for the roof water actually have fins in them to encourage the water to swirl around the pipes going down. That means they can get a much higher flow rate through them, so you need smaller pipes to drain the same amount of water in the same amount of time. So for me, that's just one example of the innovation that actually goes into everything we do at McLaren, including draining the water off our roof, for example. The sheer glass screen you see running along the front there, along the boulevard, that's hung from the roof. And it's actually got wind deflectors in it to stop it blowing in the breeze. And they didn't think it would be possible to actually build that because they couldn't get the wind deflectors strong enough and also light enough so it wouldn't pull the roof down at the same time. So they got some of the structural engineers from the F1 team in, and they came up with a new template for them that they could then manufacture out of steel, which would then make those load-bearing components in the glass strong enough and light enough at the same time, so it would hold the building up and also not tear it down. So for me, this is really a really cool example of just how innovation permeates through everything we do. I dug up this really old picture to tell you a little bit about how McLaren started. So this is from 1952, and it's our founder, Bruce McLaren. He's racing in a hill climb event in New Zealand in a 1929 Austin Ulster that he and his dad had done up for racing. Bruce really started racing because his dad was into it, and he was in fact competing at this event because his dad couldn't make it. And he pleaded with his dad to say, look, I know you've entered, but please let me race because you can't make it. And his dad said, you know what, Bruce, fine. He was just a teenager at the time. He said, you can race, but take it easy, don't push too hard, don't break the car, and don't hurt yourself. So Bruce did that. He was quite good. He took it easy. He didn't push too hard. And despite that, he still managed to win the race, and that's where our competitive and ultra-fast spirit comes from, I think, from Bruce in his teenage years, starting off racing in McLaren, and he had that natural, innate talent for speed. And that's something that continues at McLaren to today. And it was in 1963, 11 years after this picture was taken, that he founded his own racing team so that he could innovate in ways that he couldn't as a driver for other teams, and he could build his own cars and then race them afterwards as well. So that's really where the beginning of McLaren was, in that kind of racing spirit and that need to innovate and build better cars so that he could in fact actually race them himself. Another more engineering innovation over the years at McLaren was the introduction of carbon fibre as a material in Formula One. So prior to 1981, where we manufactured this car here, the MP41, F1 cars were mostly constructed out of aluminium. And so far as metals go, aluminium's quite a good compromise. It's reasonably light and it's reasonably strong as well. But it does have some downsides, so it crumples pretty easily. And also, if you imagine you've got kind of the four wheels of your car, then going over curb introduces twist into your chassis, which is really bad for performance and structural integrity. And that's something that aluminium chassis are really susceptible to. So McLaren introduced this carbon fibre chassis that you see here, which is kind of starts here and finishes at the back of the engine here. And carbon fibre is a really good material because it's ultra strong, so long as you manufacture it correctly. It's ultra lightweight, and it also introduced a whole new level of safety into Formula One. So those of you who follow F1 more regularly will have seen Fernando Alonso's accident into McLaren at the beginning of last year. We were all very pleased to see that he just got out of the car after what was quite frankly an epic shunt and was able to walk away. And that kind of that being possible today is only because of the introduction of carbon fibre as a material in Formula One. So as I said, it's strong and it's light, but also it's introduced that really important safety aspect for drivers as well. So nowadays, it's ubiquitous. So we use carbon fibre all over our cars. We use it in the chassis. Every F1 team uses it. We use it in the aerodynamic parts that you can see hanging off the front, in the suspension. But also, we've transferred that technology to other industries. So that's something that McLaren's really good at. So this is a picture of the 570S, which McLaren Automotive builds. One of my favourite McLaren road cars, not just in looks, but also because it's only £144,000. So compared to some of the other cars, is much more reasonably priced. And I was going to say one day I might get there, but I still think £144,000 might be a bit out of range for a car. But what's really interesting about this is that for your £144,000, you do get a fully carbon fibre chassis in your road car. And that's something that McLaren has taken from the racing team and applied it to the automotive industry, and they're now being able to really affordably produce extremely safe, extremely light and extremely performant cars through the use of this technology. And that technology transfer is a really important part of what we do, and we do it with our software as well. So while I said we build our software predominantly for the racing team, that's our main focus. But McLaren Applied Technologies takes that software and applies it to other industries as well. So the software that I write today will eventually be applied to the healthcare industry and the chemicals industry and all kinds of the pharmaceuticals industry. And this software will be taken by MAT and applied to all these different areas. So we're contributing to those as well. Another little bit of technology transfer, so something that might be a little bit more feasible. Any cycling fans out here? So yeah, a few. So you might be familiar with Specialized. So McLaren Applied Technologies took the racing team's carbon fibre expertise and applied it to their chassis manufacturing process. So this is an S-Works McLaren with a fully carbon fibre chassis, which Specialized weren't able to produce before. But by using McLaren's carbon fibre expertise, they were able to make this entire bike chassis out of carbon fibre. And we've got one of these in the office, and you can go and have a play with it. I wouldn't recommend riding it around, but you can pick it up, and you can literally pick that entire bike up with one finger. It's absolutely incredibly light. It's fantastic. And also on the carbon fibre kind of side, McLaren Applied Technologies worked with the British Winter Olympics team on Lizzie Arnold's skeleton bobsleigh, not just on the carbon fibre side of things, but also applying aerodynamic techniques to the equipment, and she was able to use that equipment manufactured by Applied Technologies in Sochi Winter Olympics, and she went on to win gold with that. So another example of that kind of technological transfer and applying that innovation that we come up with every day in racing to other industries. So a couple more highlights for you of things that happen inside McLaren. This is a picture of our simulator, which is buried deep down in the heart of the technology centre in a very difficult to get to place. And this is a really important piece of equipment for us for two different reasons. So first of all, it allows us to very quickly and easily test out new parts for the car without ever having to actually manufacture them. So say the engineers come up with a new part, we've got new engine data from Honda, or there's a new aerodynamic component. They will build a computer model of that, which then gets loaded into the simulator, and our test drivers are able to take that out for a spin for a few laps and able to provide driver-in-the-loop feedback to the engineers as to whether that part makes an improvement in the areas that they think it will. And this is really important for us because it means that we vastly reduce our costs when producing new parts. So we can produce a part in the simulator and test it without ever having to go through the manufacturing and testing phases actually on the track, because they're extremely expensive activities, especially if it turns out that you've just built a new gearbox and it turns out it doesn't really help you at all. So that's a really important tool for us in order to reduce the cost and the time to getting new parts out to the track and making an improvement on the car. The other advantage is helping the drivers get used to new circuits. So in 2016, there was the Grand Prix of Europe in Azerbaijan, for example. That's the first time that there's been a race there. In fact, it's the first time on the Friday morning that anybody actually went out on circuit there, because they'd literally constructed the entire track from scratch in the middle of their city centre just for that one event. So our drivers, having had a practice in the simulator on an extremely accurate model of that circuit, were able to go out on the Friday morning and immediately start delivering good lap times and helping us to evaluate new parts on the car immediately with good feedback. So that's a massive advantage for us, provided by the simulator. And the final one of our innovations here is the wind tunnel. Now, the wind tunnel we actually have on site. It's actually part of the structure of the technology centre building that I showed you earlier. It was kind of assembled 2 years prior to the rest of the building, and the rest of the building was kind of assembled around it. It's great to have this kind of resource on site because it vastly reduces the amount of expense you have going backwards and forwards. And it also means that it's really, really quick for us to iterate parts in there when we're testing. So an engineer can come up with a part, design it out in the software, have it 3D printed, tried in the wind tunnel, and then get the data back within minutes from trying it in the wind tunnel, not from designing it. They can get that data back from the wind tunnel in mere minutes and then very quickly analyse whether that new part is going to be any use for us or not. So one interesting thing about this, though, is that because it is part of the structure of the building, they had to actually acoustically isolate it because it's between the racing offices and the cafeteria, and you don't want 300 engineers trampling past at 5 to 1, causing upsets in the delicate instrumentation in the wind tunnel. So there are some caveats applied to having the wind tunnel part of your building. You have to do some pretty sensitive isolation for that to make sure that you don't upset your results. But it is really useful for us to be able to have that on site and get those results really quickly. So that was really a whistle-stop tour of some of the innovations that McLaren's introduced in Formula One and some of the kind of kit that we have available. So the next thing I want to talk about is data, and more specifically big data, because I want to show you first some rough data volumes that we're dealing with, just to give you a bit of an idea. So I can't tell you exactly how much we're dealing with, but just to give you a bit of a foundational idea in terms of how much data we're actually generating. So this chart shows roughly in hundreds of gigabytes how much data we generated coming off the car for each race weekend in 2015. So it's a reasonably linear progression, but we're not growing a crazy amount. And then that line on top there is 2016. So again, we're generating more data last year than the year before, but we're still not growing at a massive rate. Now, bearing in mind this is raw data that's generated by the car, and we're downloading that off the car when it comes back into the garage. Now, the reason that we're not exponentially growing this data volume that we're generating, and trust me, the engineers would love to. They'd love to collect loads more data. But the reason that we don't do that is because of a constraint of the industry, and that is that the performance of your car is a function of how heavy it is, and the more data that you want to record off the car, the more mass you have to add to the car to do that actual recording. So say you want to measure some new suspension bit. I don't really know much about suspension, as you might be able to tell. But say you want to measure a new suspension bit. What are you going to actually have to do to be able to measure that? Well, you're going to have to put the actual sensor on the car, so that adds weight. You're going to have to wire it up to the battery, so it has power, so that adds weight. You're going to have to wire it up to the computer on the car, which adds weight. So in F1 terms, when we're talking about adding a meter of one wire to the car, then that's deemed as a significant amount of weight that we're adding and costing us performance. So that's the kind of thing we need to consider. And once you've reached a certain amount of capacity on your storage unit, you then need to add another one to the car, which is then another load of weight which you have to add. So the reason that the amount of data that we're generating on the car isn't spiking up massively through each season is because we're constrained there, and we can't just go adding sensors willy-nilly to the car. So that is where we're capped. This chart, however, in contrast, doesn't show the data generated by the car. It shows all the data generated not on the car. So this is the result of things like offline simulations that engineers have run. It's all of the configuration information that we store. I don't think it includes like video and other media, but it definitely includes things like all of the configuration data, all the metadata, and all the general bits and pieces that engineers generate off the car, so in addition to the telemetry that we receive on the car. Now, as you can see, we're still talking in the hundreds of gigabytes, so it's actually not a massive amount of data. If you're talking to Facebook or LinkedIn about how much log data they're generating off their servers, for example, they're talking about terabytes of data. So we're still in the hundreds of gigabytes per race, so it's not an unmanageably large volume. It's a bit spiky, and that's because of our use case. So some weeks they'll be investigating different parts of the car, and some weeks we might not have any new parts, so there might not be any really big investigations going on. But we're still growing the amount of data we're generating. But what's interesting, if I break this down very quickly, so the red line here is how much data the aerodynamics guys are generating, and the blue line is how much literally the rest of the office is generating. And you can see that for all but one race, I think, the aero guys generated way more data than the rest of the office combined. And you can see why that would be, given the complexity of the nature of their simulations. If they're modeling 3D space with a load of data points in it over time for an entire lap or an entire race, then it's very, very easy to build up a massive amount of data that you're generating and storing there. But as I said again, it's not an inordinate amount of data. It's not unmanageable. It's still hundreds of gigabytes, but it's not unmanageable. So if our data isn't big in terms of its size, then why do I say that we've got big data? Well, the answer to that question is data complexity. So there are a number of ways that our data is extremely complex. Now, you might not necessarily think that, because you think, well, if you're just reading sensors off the car, then surely it's just a stream of numbers. You're just dealing with just essentially really big lists of doubles, right? And at the end of the day, then yes, you essentially are dealing with really big lists of doubles. That's what it boils down to. But there's some aspects of that data which does make it very complex to deal with, and I'll explain a few of them now. So the first thing to consider is the huge variety of sources of data that we actually have. So this is an F1 car on a track, and that does generate a lot of data, hundreds of gigabytes as we've seen. But it's only one of a huge myriad of sources that actually generates data that we need to analyze together. So consider, for example, the simulator. That generates telemetry data, just like on the car does on the track, but it's not constrained by only being able to run when the FIA says we're allowed to run on the track. So we can run that whenever we want, almost within limits. So that's generating telemetry data as well. We've got the wind tunnel, which I've also shown you, which is generating aerodynamic telemetry data, which is, as I said, in 3D space over time, which is a huge data set there. If you also consider computational fluid dynamics, or CFD, which is modeling the aerodynamic parts on computers, that's generating a massive amount of data. And you've got our simulations as well, which engineers are running on a near constant basis, so it turns out. That's generating a vast amount of data. And the engineers need to be able to analyze that data together. They need to be able to correlate CFD with the wind tunnel, with the track. They need to be able to say that, yes, when we're building a model in CFD, and we're running it in CFD, and then we build that part and put it in the wind tunnel, and then we run that part on the track, we're getting the same results every time. And they need to be able to analyze that data together. And it's only when you add all of these disparate sources of data together that you get that layer of complexity of normalizing all of that data so the engineers can understand it and analyze it together. And that's where the first of those bits of data complexity comes from. The other thing to bear in mind is that a lot of the data is completely meaningless without the correct context. So my favorite example of this is thinking about tire temperatures. So at the very simplest case, if you wanted to look at the tire temperatures of a car, you're basically loading up 4 parameters, 4 lists of doubles, one for each tyre as it goes around the track. So say you're looking at 1 lap's worth of data, and you say, okay, well, I've got 4 channels worth of data, and these are the 4 tyre temperatures. That's fantastic. So that's pretty easy to analyse, right? You've just got 4 lists of doubles. But in order to actually get any useful information out of that whatsoever, the engineers need a whole myriad of contextual information in order to check that that data correlates with their models. So the first thing is you've got 4 channels and you've got 4 tyres. Which one's which? Which one's the front left tyre? Which one's the front right tyre? So you need to figure that out for the first thing. You then also need all kinds of information about the car itself. So at the simplest level, which car was it? But also more complex information like which suspension configuration was it running in? What ride heights were set? What actual parts in the suspension were there? Which specific tyre set was it that we were running? out of all of the ones that are available to us at the weekend? What tyre compound was it? What were they preheated to before they went out on track? What tyre pressures were they set to? What rims were they attached to? What was the presentation angle of the tyres? So that's just the data about how the car has the tyres attached to them. But then you also need to consider things about the environment. So what was the air temperature at the time? Because that will affect how the tyres are performing. What was the track temperature? Was it raining? What circuit was I at? And all these other things. So where were the corners? So you need to take this vast amount of metadata and compose it together, and you're eventually dealing with 10 or 50 times as much data for the context than you are just for the actual telemetry to give you the tyre temperatures. And you need all of that data together in order to make sense of it and make a meaningful comparison of those tyres between different runs and even between different laps. So the complexity of the data is really high due to that amount of metadata and additional information you need in order to understand what you're actually looking at. So when I say we've got big data, it's not necessarily a huge amount of it, although it's still quite a lot. But it's that complexity that makes it much more difficult to work with. And it's only when you have all of that data together that you can actually make any sense out of it. Excuse me. So that's why we've got big data. What do we actually do with it, though? So I've talked a little bit already about our acquisition phase, which is attaching sensors to the car, logging them on the car, and we also stream some of that telemetry to the garage, and we'll also save some of that telemetry to the car, so we download it when the car comes back into the garage at the end of a run. Transmission is actually not always an easy thing to do. Fortunately, most of this is managed for us by McLaren Applied Technologies, as they do for all of the teams on the grid. But I've included a picture here specifically of the Belgian Grand Prix for a very good reason. Now, acquiring radio telemetry at the Belgian Grand Prix is always a little bit tricky because it's in the middle of a forest and trees don't happen to let radio waves through them all that easily. So you end up with data holes in the telemetry. But it's also another good example for the other aspect of data transmission we have. So the car itself is recording data and streaming it back to the garage. You've got an engineer in Woking, in the office, who wants to look at that data so that he can help the team at the track with a specific piece of analysis that he's an expert in. How do you get that data from the middle of a forest in Belgium to Woking? Well, it turns out with a reasonably high level of latency, because you don't get great connection out there, and you also have reasonably high latency to far-flung corners of the world. So Brazil, Australia, China and Japan are typically examples of high latency scenarios. And that can be a challenge when you're trying to either A, stream real-time telemetry back, or B, copy what could be tens of gigabytes worth of data back to the factory for the engineers to analyze as quickly as possible. So we actually had to build our own data transmission system for the simulation results in order to cope with this kind of scenario, so that engineers who are at the factory and at the track can run their own simulations, set up their own configurations, and collaborate in near real time with the engineers on the other side of the world, potentially, so that they can then work as effectively as possible. So there are actually some quite big challenges in this area that we have to deal with, not least of which is the fact that every week the half of the office disappears to a different location in the world. So once you've got it working for Belgium, that's all well and good, but the next week you'll be in Italy, 3 weeks later you'll be in Azerbaijan, and then you'll be in Brazil. So you have to have that infrastructure to be able to deal with that kind of situation. My favourite example of a problem like this was a couple of years ago when I was covering the Monaco Grand Prix. We had an issue with the trackside infrastructure. So we have a rack of servers in the back of the garage that travels around the world. And while we were doing all the setup, every few minutes the database server disappeared. And then it would come back again. It's like, well, where's the database server going? So he got in touch with the IT guy at the track, and he did quite a lot of digging. And about 20 minutes later, he came back and said, you know what, I figured it out. Every time the database went down, a forklift truck had just run over the cable in the back of the paddock. So they had to reroute the cable over the top of the paddock rather than around the floor, because the forklift truck kept running it over and pulling out the cable, which was causing outages for us. So it's that kind of thing that we have to deal with on a weekly basis to see whether our infrastructure is going to hold up. So the final topic in that kind of flow of the data, once we've collected it, transmitted it, and then we have this exploratory analysis phase. Now, this is interesting to talk about from a software perspective, because recently there's been a really big and really valid push towards building apps that do one specific thing and do it really, really well. And helped along, of course, by mobile devices, your iPhone. You launch an app, you press a button, and then a taxi turns up. That's pretty much as easy as it's going to get. And that's great, but we can't necessarily do that all the time when we're developing software for F1 engineers, because a lot of the work that they'll do will be exploratory. So say you've just had, say it's just before qualifying on a Saturday afternoon at the Australian Grand Prix. Okay? It's 3 o'clock in the morning in the UK, and an engineer at the circuit has just come up with an entirely novel piece of investigation he wants to do with your software. He wants to get it done before qualifying. What you don't want to have to do at that time is write and deploy some software that solves that specific problem for him. First of all, because it's 3 o'clock in the morning, and that's never a great time to be trying to write and deploy software. And second of all, because you're probably not going to get it done in time. So we have to build in from the beginning a sufficient level of flexibility in our core application so that engineers can do that exploratory analysis themselves without having to wait for us to build something new for them. So that actually introduces a reasonably high level of complexity in the software that we produce. And when I first started at McLaren, I must admit they showed me the way that you choose which pieces of data you want displayed, and it took me about 20 minutes to figure out how it worked, despite the fact it was basically filtering and then clicking a button. Because it's just the inherent level of complexity in choosing exactly which parameters you want displayed and how you want them displayed is something that the engineers need sufficient flexibility to be able to do in any which way they happen to fancy at whatever time of day it is. So some of our software isn't intuitive, but it does maintain that level of usefulness to the engineers so that if they do turn around and say, I've just come up with something brand new and I need to analyze it straight away, they're able to use our software to do that without having to make too many modifications to it. So exploratory analysis is a really important part of what the engineers do, and we have to bear that in mind when we're developing software for them so that they're actually able to do their job without us having to make massive modifications to the code. Okay, so that's a bit about our big data, big in terms of complexity, but not necessarily in terms of size. So next up, I'd like to briefly walk through a few of the things that we do as part of a race weekend in order to help the team. So this here is a picture of what we call mission control. It's another room buried in the technology center, very difficult to get to. This is our central nerve center, if you like, for race operations in Woking. So as you can see, we've got quite a lot of data available to the engineers in there. So you've got the live TV feeds from the circuit. You've got things like our circuit tracker, so you can very easily see where everyone is on the lap, all of the data around lap times and so on. You've also got things like the live telemetry feeds coming back into mission control. So if you're want to look at the data live, then mission control is the place to go because it's linked directly to the track. And you've also got the radio panels here, which allow you to interact with the engineers at the circuit, just like they were sat next to you. And in fact, if you're sat in mission control, then you most likely will be interacting with engineers sat next to you and at the circuit at the same time through your headphones. And it'll be like you're just sat next to each other having a conversation like you would be in the office on a normal day. And that's a really important part of the collaboration that we do in order to make sure that we can work effectively over the weekend. So for us, a race weekend doesn't really start on Friday. It starts much earlier than that. So by the time we get into the Wednesday leading up to the race, at that point we'll have done most of our preparation work. So that means having the final builds of all of the software that we're going to use for the race weekend, ideally. That all needs to be built, and it also needs to be deployed, not just to the factory, the technology center for the engineers there, but also to the track as well. I mentioned earlier, sometimes it's a long way away, and sometimes the connection's a bit slow, and sometimes you do have quite a lot of software that needs to be deployed. So that's something that needs to be thought about in advance. The other thing to bear in mind is that the engineers will turn up and work, for the most part, during the day in the time zone at the track. So that means if they're in Japan, they'll typically turn up at the circuit at 11 p.m., midnight, UK time, to start their working day. So you need to have the software deployed ready for them when they turn up at the track to install the latest version and then get working. So you do need to think about that sometimes and make sure that you're fully prepared in advance. And that does mean some early mornings, as I said. So by the time we get into Wednesday, then we look to be fully prepared and ready to go, and everything should ideally be set up ready for the race weekend. So on Thursday, there's no on-track action, so to speak. There's a few little bits and pieces that happen for the FIA, but we won't be running the car on the circuit. But Thursday is still a really important day for data collection, and that's because Thursday is when they're finishing off assembling the cars ready for the race weekend. And while they're doing that assembly in the garage, which is what you can kind of see going on in the background here, while they're doing that assembly, they'll be testing specific parts of the car. So they might be testing the gearbox, they might be testing the hydraulic system, the clutch, they might test the engine, they might do strain tests on the suspension, and they'll do setup tests on the entire car. And that data is really, really important for the engineers at the factory to be able to start their correlation analysis, check the parts are working correctly. And so our software needs to be fully ready at this point to be able to collect that data, distribute it, as we discussed earlier, to the engineers at the track and at the factory as well, so that that important engineering can happen, so that when we turn up on Friday, we know exactly how all of the parts are set up and things are going to work correctly when we get there and start going out on the circuit. So Thursday, well, there's not much happening for viewers, then there is a lot happening for us, and we need to be ready and working on that. So practice starts on Friday morning, 90-minute session. There's another 90-minute session on Friday afternoon, and there's a 60-minute session on Saturday morning. And I will admit that practice sessions, unless you're really, really into F1, aren't necessarily the most riveting TV viewing. Okay, they tend to be lots of drivers going around moderately slowly, doing 1 or 2 laps, and then going back into the pits, and then frantic engineering on the car, and then another couple of laps afterwards. But for the team, this is a really crucial part of the weekend, because during practice, we're allowed to run parts that we wouldn't normally run as part of the race weekend. And it also means it gives us an opportunity to test out new parts on the car. Now, what that means is that we're likely going to be doing loads of very important experiments this time, which means that the telemetry that the car generates is very, very important to engineers, not just at the track, but at the factory as well. So our software needs to be collecting that telemetry, analysing it and distributing it to the engineers as efficiently as possible, because we want to know as soon as the car comes in, and maybe even before, that a new part has worked or not, so that we can then advise the engineers at the track whether they need to take it off or put something different on, or whether they're going to leave it. So practice sessions are really, really important for our software to be able to determine whether something is working, and the engineers need to run that analysis and answer the track very quickly as to whether we're going to take that direction forward, say whether that new front wing has given us the amount of downforce we thought it would, or whether it needs to be taken off, we need to try something else, or we need to trim it or modify it or something like that. And we need to really tighten that feedback loop, so it's important our software is working as quickly and as efficiently as possible during that time to get that data transferred. So on the Saturday afternoon is the qualifying session, which determines your grid position for the Sunday race. And this is a very different mode of operation, both for the team, for the car, and for our software. So the rules of F1 mean that once you first go out in qualifying, you can't make really any major modifications to your car after that point. So during practice, you're going to be changing a lot of parts and optimizing your setup, but once you go out in qualifying, for the rest of the weekend, you can't really make any big changes. So that switches the mode of operation for our software from this analysis job, where we're looking at whether those changes may affect the car, to trying to improve the performance of the car in a very different way. In qualifying, because you can't change the car, the biggest lap time improvement you're going to find is by helping the driver to drive a much faster lap. So by improving how they're driving the car, the line they're taking, the steering wheel angle they're putting in, the throttle and brake timings, all these different things. If you can help the driver to improve his lap time that way, then you're going to get much bigger gains than you can by any of the other tweaks you can make to the car. So our software switches focus towards producing a specific chart. So if you ever watch a qualifying session, you'll see when the driver comes in after doing a fast lap, they're pushed back into the garage, then a screen's taken down. It's either a screen taken down and put in front of them, or an engineer turns around and gives them a piece of paper. Now, the screen and the piece of paper are just different ways of delivering the same thing, which is what we call an overlay chart. And that chart shows them a comparison of the last lap that they did, their last fastest lap, with another lap. So it could be a lap from earlier in the day that they did, it could be a lap from practice, or it could even be a lap that their teammate has just done as well. And that overlay comparison shows them data that kind of looks like this. This is just some fudge data that looks a bit like car speed. But in addition to car speed, we show them their steering wheel angle, their braking acceleration inputs, when they changed gear, whether they had the DRS flap open, and all kinds of other different parameters that you get from the car. And we compare that with the other lap so that they can see, well, actually, through this corner, say, Stoffel might say, oh, Fernando gained time in corner 7 because he got on the brakes a bit later, but I gained time through turn 8 because I took a slightly different line and I turned in slightly earlier. So those are the kind of pieces of information we're trying to deliver to the driver in qualifying. And for us, it is literally a race for us to be able to produce that data, that chart and that analysis so that they can have it as soon as they come back into the garage, because it can be as little as 30 seconds between them being pushed back into the garage, tyres changed, top up of fuel, and then they're off again. And they need to have had that data and learnt what they need to before they go out again. So once the car crosses the start-finish line at the end of their fast lap, it's literally a race for us, because we have to download the live telemetry from the car, we have to import it into our software and import the other lap that the engineer has chosen, so maybe from the other driver. We need to do the comparison to see which one was faster, and then we need to compare that data and show them which bits were different. We then need to send that to the printer, wait for the printer to print it out potentially, and so that the engineer, ideally, picks it up out of the printer and turns around and gives it to the driver as soon as he's back in the garage. That's the ideal case for us. And it's as little as 60 seconds that we have at some circuits to be able to do that. So we all love covering Austria because it's such a short lap that by the time they cross the start-finish line, we barely know what's happened and they're already back in the garage. So that's always a bit of an adventure covering that one. But that's the challenge that we have to deal with in order to improve the driver's performance through qualifying as much as possible. And that's what our software does. There we go. So I will briefly mention the race, although I won't go into too much detail, because in the race you can change even less than you can in qualifying. In the race you can choose what time you want to have a pit stop, what tyre you're going to put on, and what front wing angle you're going to change, and that's basically all you can change on the car. So once you get to that point, you're about helping the driver and managing any issues on the car, but there's not really that much analysis work that you can do on top of that, other than by analysing the live stream of telemetry coming in, which is handled by other software. So for us, the race is just about helping the driver as much as possible. The engineers will still look at those overlay comparisons to help them improve their driving if necessary, especially if it's at a newer circuit. But for us, the real meat of the Sunday starts after the car has come back into the garage. So are most people familiar with the term back-to-back races? So a back-to-back race is where you have a race on the Sunday, and then the next race is the next weekend. So you're in one country on the Sunday, and then you're expected to turn up and be ready to go out for practice on the very next Friday, 5 days later. And so when we have a back-to-back race, all of the kit in the garage has to be torn down very quickly at the end of the race. So that means all of the server infrastructure, which happens to be storing the data from the race, is basically unplugged and put in a crate for 4 days. And we need to make sure that we efficiently synchronize that data back to the factory so that engineers coming in on Monday morning are able to do their analysis work with the latest and most correct data. So for us, it's a bit of a race once the car comes back after the end of the race to get that data offloaded into the garage and then as quickly as possible back to Woking so that that kit can be switched off and shipped to the next circuit. Okay, so that's an outline of what we do throughout the race weekends. And so the final topic area to talk about is a little bit more in-depth, and it's about how we develop software and essentially our software development processes. Now, we've been modifying our development process extensively over the past few years in order to be able to deal with what I described earlier, which is an extremely fast-paced, extremely engineering-focused industry. And so we've made a lot of adaptations. It's almost like you can envisage us starting with something like Agile, and then basically on an almost weekly basis saying, oh, this bit isn't working for us, let's tweak it. This bit isn't working for us, let's tweak it. This bit isn't working, let's tweak it. And we've kind of ended up with where we are today, which isn't really any one specific methodology. We don't adhere to one methodology by the book. What we do is develop software in a way that's suitable for our industry and delivers the results and the software when we need to for each race weekend. Because there's one thing about Formula One is that if your software isn't ready, you can't phone up Bernie and ask him to hold the race on the Sunday afternoon. It's not going to happen. The race is going to go ahead whether you're ready or not, whether your software is deployed or not, or whether it's built or not, whether you've even finished writing it or not. So there is one thing that we have to deal with, which is these very hard deadlines. And I think We Must Move at the Speed of F1 summarizes how there are these hard deadlines, and if you don't make it, you're not going to make it, and it's just not going to happen. Things aren't going to wait for you. You can't phone up ops and say, you know what, we're not quite ready, let's do it on Monday, because the race is going to happen anyway. The other thing is the pace of innovation in Formula One is so high that we have to very rapidly and frequently modify our software to be able to deal with these constantly evolving requirements. Engineers would always come up with new pieces of functionality they want, new things they want to do with the software, and so we need to be able to handle that. And part of that is about working in an agile way and taking on these recommendations. Part of that is about having an extremely rigorous testing process to make sure that we don't break other features of the code when we're rapidly iterating in another area. For example, I talked earlier about the chart that we generate during qualifying. Heaven help you if you break that and don't realise until Q1 on a Saturday afternoon, because then you really are in trouble. So we have to make sure that in addition to moving quickly, we're balancing that with a sufficient level of testing to make sure that we're not deploying software that's going to cause problems in important areas throughout the rest of the code. Another interesting aspect of the work that we do is that we only produce software for F1. In fact, specifically, we only produce software in our team for engineers on the same floor of the same building as us, and because it's a very long room, in the same room as us. So some of our software, so our most used software has about 260 users, and if I stand up at my desk, I can see 80% of them at any given time, probably, just by turning around and seeing their heads popping over the edge of the corrals. Our least used software has maybe 5 users, but they happen to be the race engineers, so they're quite important. So that's a different challenge entirely. But all of our customers, in addition to being in the same room as us, they're all extremely highly trained, very switched on engineers. So one example is they often specify problems to us in the forms of, why didn't you build me this solution, rather than explaining what the actual problem is, so that we can then actually potentially build them something that's more correct. So often they'll come up with this and say, I'd like you to build this, where what we really want them to say is, I'm having this problem, and then we'll help them solve that in the best possible way. Another thing since I've started at McLaren a few years ago now is that my engineering vocabulary has expanded significantly. They will happen to talk to you in the terms that they use on a day-to-day basis with the rest of their engineering teams, which means that I now know some very specific aerodynamic terms and some very specific systems engineering terms that I never thought I'd need, just in order to understand them stringing 3 sentences together and explaining what they want to actually happen. So they have a very specific domain knowledge, and it's not just, there's not like one Formula One domain dictionary, if you like. There's one for aerodynamics, there's one for systems, there's one for the hydraulics guys, there's one for the gearbox guys, there's one for race engineering, and they all have their own different terminology. They do overlap in places, they often don't contradict each other, but they all have their own kind of areas of expertise. And when you first start and they kind of say 2 sentences and you're stood there going, I have literally no idea what you're talking about, it is a bit of an adventure to then eventually learn all what they're describing and what they're trying to explain to you, so that you can actually build the right software for them. So that's a really big challenge. So another challenge for us is support. So most of the time, if you don't consider race weekends, most of the time support isn't the end of the world, because if there's a problem, they'll inevitably pick up their laptop, walk over to your desk, put it down and say, this isn't working. And that's reasonably easy to deal with. I mean, it's not ideal to be interrupted, but you can work on it, you can tinker around with their machine, see what the error message is, and so on and so forth. But when you've got the engineers who go to the track, they expect the same level of support for the software if they're stood in the garage in Azerbaijan as if they are sat at your desk in Woking right next to you. So we've had to do a number of things to be able to deal with this within our software and within the way we work. So I've already mentioned that we have an engineer on site throughout race weekends. That gets especially interesting in testing when it tends to be kind of 20-hour days. So we try to do that in shifts when we're in Woking for that. But we've also implemented some functionality in our software in order to help that support easier. So our goal at the end of the day with the support is to go back first time with the right answer and in a timely way. So when someone says, I've just tried to do this and it hasn't worked, we aim to go back to them first time with either, ideally, a solution, if not a workaround, with something that they can do instead. Sometimes I'm sorry, this is broken, let me just check in a fix and get it to you tomorrow. But that's what we're aiming for here. And in order to facilitate that, we've actually integrated into our software reporting functionality, so that instead of them doing what they used to do in the old days, which was either send an instant message, send an email, or if it got really bad, yell at us over the radio. They now have a button in the software, which is basically, I've just tried something and it hasn't worked. And that gives us an opportunity to type in very briefly what they were trying to do and why it didn't work. And then when they send that, our software captures a vast amount of data and sends it up with that report and sends it to us straight away to our help desk software. And what that means is that we are able to very quickly diagnose problems and come up with the correct solution. So all of the logs are shipped, for example, straight away, so we can view those remotely. All of the state of their application running on their machine was sent at the same time. So we are very quickly able to reproduce exactly what they've done. In fact, we can have exactly the same piece of data open that they had open. We can click exactly the same button and, ideally, reproduce and fix the problem much more easily. So that's kind of the journey we've been going on over the past few months in order to help the engineers who are at the track in a situation like this, because this is, I think this is probably during practice, but at this time, who have we got? So we've got the drivers, we've got Fernando and Jensen, this is from last year, and you've got the chief engineers and Ron over at the back here, but the four engineers that you see here, so you've got Mark and Will for Fernando, and you've got Tom and Angel for Jensen, they will all most likely be using our software at that point in time to do critical analysis ready to go out for the next run. So when you're in that situation, you need those guys to be able to get help quickly and get the right help as soon as possible. Unfortunately, we've been able to do that now, so over the past few races, in the past few months, we've definitely been able to help them much more efficiently due to those introductions we've made to the software. So I'm not going to spend too long on this because I did promise you some time for questions. I don't know if there's loads of people itching for questions, but I will just go through this briefly. So in terms of what we actually do on a day-to-day basis, some highlights of that. So 1 week sprints. So we kind of kept the sprint concept because it's useful for us to kind of split up our time in that way. By doing 1 week, it means that we are able to rapidly take on board issues from race weekends. So we'll have someone in over the weekend, and then they'll hand over to us on Monday morning the issues that came up. And then that will be the opportunity for us to incorporate them into the work that we're doing for the next week. Because if you are on a back-to-back race, you need that software ready to go on Wednesday. So if there was an issue over the weekend that critically needs fixing for the next race, you better be looking at that at 9 o'clock on Monday morning and getting that fixed, prepped, and ready for release the next week. So we keep it at 1 week because any shorter than that would be ridiculous, and any longer than that, and we wouldn't be able to adapt to the issues that come up frequently throughout the year. So we have a weekly ship room. So if you're not doing support, on Friday afternoon, we take time out to have a retrospective on the week. And that isn't really a retrospective of what we did, as in what code we wrote or what bugs we fixed and so on and so forth, but really it's also a retrospective on our process. So I mentioned earlier how we rapidly evolve our software development process. The weekly retrospective ship room is an opportunity for us to do that. We'll look back and say, well, actually, we didn't realize until halfway through the week that X needed doing, and the reason we missed that was because someone reported it by email to person Y rather than actually using the built-in reporting system, for example. So that will then lead to a change in process about people reporting issues, which will then help us to improve. And because we do that on a Friday afternoon and we have 1 week sprints, that can take effect from the very next Monday morning, and we can incorporate that into our process straight away. So I'll talk about releases in a moment, but managing changes is something that comes along with part of the 1 week sprint. So as I mentioned, bugs might come up on a Sunday and you need to start looking at them on a Monday, which is fair enough. But sometimes issues come up during a sprint as well. In fact, reasonably frequently. As I mentioned, the engineers are constantly exploring and trying to do new things with the software because that's what their job is. So issues can come up throughout the week as well, and maybe problems that were had over the weekend won't be reported until the Monday or Tuesday when they land back in the UK. So in order to manage that kind of change, we always allocate maybe half or a whole engineer week out of the team in order to deal with those issues that come up. Even if it's not fixing them all, then it's at least properly triaging them and making sure we have proper bug reports for them and so on and so forth. And it's that managing that change which is part of what we do, and incorporating that into our planning means that we're not, well, unless something's gone catastrophically wrong, we're not typically caught out by it too much. And the final point at the top there, embracing MVP, is something that we actually do in more than just features. So MVP is typically used, the minimal viable product, to produce use as small amount as work as possible to produce a feature that's useful to your users. Now, of course, we do that with our features, but we also apply that to a number of other areas. So, for example, in terms of bugs, we'll apply MVP to bug fixes, especially over race weekends. So say a piece of software isn't working on a Friday morning, and we know we're going to need that in qualifying. What you want at that point is a fix that solves that specific use case, that specific problem that's not working, without causing loads of regressions all over the rest of the code. And the question you ask yourself at that point is, what's the minimal impact change I can make which resolves this issue and allows the software to continue functioning in this use case, and also in the potentially thousands of other use cases that it's going to be put through at the same time? So we apply MVP to bugs, and also our process. We're always asking ourselves, can we subtract process and still work at the same level of efficiency? We don't want to be spending all our time in meetings trying to figure out the best way to develop software, because we need to spend our time developing the software. So we'll take as much process out as possible while still allowing us to continue to function efficiently. I'm going to slip over that slide because I want to leave plenty of time for questions. I think this answers someone's from earlier on, which is that we do have a software engineering role, permanent position open at McLaren at the moment, doing what I've just been talking about. So if you think we're not a barrel of crazy and you're interested in this kind of thing, then it's not on the careers website at the moment. It will be shortly, but if not, just send me an email and I'll be sure to put you in touch with the right people when we come around to putting it on the website. So if you are interested in this kind of thing, I would strongly encourage an interest in Formula One, because that's where a lot of the benefit comes from. Then you're more than welcome to get in touch and I'll put you through to the right people. Okay, so that's it. I've got time for a few minutes for questions now, I think. Yep, 5 minutes for questions. Again, if you do have some more feedback than red, yellow, green, then please just do feel free to send me an email or a tweet, and I'll get back to you as soon as possible. I'll also be around for the rest of the week, including tomorrow night, so feel free to walk up to me at any time and pester me about anything I've talked about. But is there any pertinent questions that people have now based on what I've just been talking about? Really? That's never happened before. Yes, a question. Hello. Questions about, do we have any software that's deployed to the car? So the cars run a standard ECU, standard unit provided by Applied Technologies, which is provided to all the F1 teams. So that has its own tool chain for developing software for it. So we don't really have to do any of that because it's provided to all of the teams the same. So we provide some software on top of that for managing that process, but we don't actually provide anything that gets directly run on the car, because that's a bespoke piece of equipment that McLaren Applied Technologies provides to everyone in F1 and also everyone in NASCAR and IndyCar as well, I think. So that's kind of a standard thing that we don't really have to get too involved with. It's also, oh yes, next.
So out of all the software you described,
Yep.
which software is actually written in .NET?
Oh yeah, I should mention that, shouldn't I? So, on the grand scheme of things, I'd say about 80% of our software in total that I've talked about is written in .NET. And the advantage of that is that we don't have to really worry too much about the deployment of it, because we've all got Windows boxes and we write it once and it works everywhere. There's quite a lot of desktop analysis software, which is easy for us to develop in .NET, because it provides a decent UI framework and it makes it easy to deploy and batch it all up together. So yeah, I didn't really mention that, but actually the vast majority of it is .NET based, and for that reason that it's very easy for us to build it and deploy it, if you see what I mean, because we don't want to, as I mentioned, we're working at a very fast pace, and we need to get stuff pushed out quickly, and so we're not looking at working in systems that slow us down, whereas for us we find that .NET and specifically C# allows us to work quickly and innovate by adding new functionality or modifying existing code quite quickly and easily. It also allows us to build in that level of flexibility that we need to. We can very quickly diversify a system out to work in different areas by exploiting that kind of technology. I think that's a very short answer to what could be a very long-winded explanation there. So that's just a summary, really. But I think that's the main reasons why we kind of work that way. Yes?
How much appetite do you have for using the latest technology as opposed to very old technology?
Okay, so how much appetite do we have for using the latest technology over things that are old? And do you say stable or stale? Stable. May well be the same. May be the same point. So we have a very strong appetite for new technology. So there's a lot of things that I'd love to tell you about but can't. where we're innovating in some really interesting areas, and that kind of I couldn't really go into much detail with it in the talk, and only hint at it with the kind of introduction on the innovation that we do. But we do aggressively adopt new technology where it is a performance advantage for us. Obviously, sometimes we just need software to be rock solid and absolutely stable, and it's worked for the last 3 years, and it's going to carry on working, so there's no need to go messing about with it. Conversely, if there's a new paradigm or a new way of working or a new methodology or whatever, and we can see that or we think that's going to provide us with an advantage, then we'll go and investigate that, and if it does, then we'll go and invest heavily in that area because for it to bring us a competitive advantage, and so long as it does. So there is a very strong appetite for it, yeah. Hello.
Is it your software on the telemetry devices? Can you tweak the amount and type of data that you get back during the race?
So is it our software on the telemetry devices, so on the car, and can we tweak the amount of data that we get back and the type of data during the race? So it's our configuration on top of the applied technology software that's running on the car. It's not allowed within the rules to modify that while the car's on track, but it is within the rules to modify it between runs. So we'll set it up in a specific configuration of the data that we want to receive, and then that will be the configuration that's used until the car comes back and we reconfigure it, essentially. I think that configuration might be subject to Parc Fermé, which means when you go out in qualifying, it's then fixed for the weekend. But certainly when you're in practice and you've put an aerodynamic rake on, then you're going to have to change your configuration so you can log the data from that rake, maybe transmit it back so the engineers can look at it straight away. So certainly you do need to modify that sometimes on a per-run basis, but you can't modify it while the car's on the track now. It's technically possible, but prohibited, if you see what I mean. Hello. Which frameworks and libraries are we using on top of .NET? So, sorry? Third-party ones. So we use a reasonable amount of Microsoft kit, I'm not going to lie. Some of our older applications use things like MEF and Prism, especially when they're running desktop UIs. It's not necessarily trendy or cool, but it is stable and working, which is the other side of the flip side of the equation. So there's always the question of technical debt when you're introducing new things. So the MEF and Prism stuff is good for us because it's easy to maintain and pretty reliable. I mean, you don't want to introduce a new library that then turns out to be an absolute pain 3 years down the line. So there's a whole lot of stuff that we use, but because what we do is actually really, some of it is really quite bespoke. It's kind of both ends of the scale. We have stuff that's kind of plain old, everyday development that you'd find almost anywhere, and then you've got the other end of the scale where it's this weird bespoke stuff. And sometimes I find myself with a user story, which is like, I'm just sat there going, okay, well, I'm going to need a book to figure this out, like an engineering book or a mathematics book to figure out what I've got to build here. And there's some stuff which is like you're updating a database or whatever, something that everybody does almost every other day. So for that kind of everyday stuff, then we'll use typically off-the-shelf stuff that we know is reliable and will get the job done. And then for the more bespoke stuff, we actually have over the years, we've built up a vast library of internal software that, if we don't use it, will at least be the foundation or the inspiration or give us the technical implementation direction for what we're trying to do. So whether it's a specific algorithm, there will probably be an implementation somewhere in the company if it's not available in a library. So we'll reuse that implementation or translate it or whatever, whether we need to. Okay, I think that's nearly time. So a couple more questions. Yep.
Wondered if the work that you do ever impinges on the strategy or tactics during a race, so how it might affect the way the driver drives the temperature.
So the question is, does what we do ever interrupt or cause problems with the strategy during a race, or how the driver drives during the race? Causing problems for the driver during a race is generally a no-no, and that's something that's one of our main priorities to avoid. So you don't want to break stuff that's going to cause problems for the driver. Fortunately, once the driver's out on circuit, our software can't really do much to affect it because, as I said, we can't send stuff to the car. So once it's out, unless there's a pre-coded problem or something breaks, then it's very difficult for us to cause too many problems, fortunately. You don't want to produce software that's slow or unreliable for what the engineers are trying to do to analyze the car while it's on the track. So you don't want to be introducing performance problems in that code, and they suddenly find that a piece of analysis they used to be able to do between the car crossing the line and getting to the end of the first corner now takes them from the car crossing the line to the end of the second sector, 2/3 of the way around the lap, because they don't then have time to tell the driver to get into the pits, for example. So you've got to watch out for that kind of thing off the car on the user's software that they're using, for example. So yeah, I think we can't break the car, but we can introduce problems in the software which reduces the operational effectiveness of the company and the team, which can cause that kind of problem. So that's one of the main things that you seek to avoid. Yeah, as I mentioned earlier, don't break code that's used during qualifying, or similarly, don't slow it down too much, because then that's a problem. Hello.
Since you're doing 1 week sprints and it all has to be done really fast, do you still use this old approach of an analyst analyzing the problem going to the developer?
So the good news is that we have the engineers who are specifying what they want, so they have a very good technical understanding. So they might not be software engineers, and they might not necessarily be coders, but they do have a strong technical background. So that's one of the things I actually enjoy most about what I do, which is collaborating with those engineers and understanding what they want, having them express their engineering problem in terms that they understand, and then working with them to do that translation into a piece of software, whether it's a design or a first initial implementation or a wireframe or whatever it is, that shows them how the software will solve that problem for them. So we don't necessarily use analysts, but we will kind of supplement that role by the user and us coming together to kind of perform that work without kind of an intermediary, if you like, because we know what they're talking about to an extent, and they know what we're talking about to an extent, so that kind of collaboration, I think, excludes the need for that. And also, again, the time. We don't necessarily... What we try to avoid is people coming along on a Monday or even a Thursday and saying, I've just had this great idea for a completely new piece of software, I need it tomorrow. Yeah, so people tend to understand now that kind of isn't going to work. Whereas, we've had stuff where people have, this year, people have asked for new pieces of software on the 4th of January because they've been thinking over Christmas, we should do that. And we're going to deliver it for the first test in, 4 weeks' time? I should probably know. In retrospect, I think it's 3 or 4 weeks' time, and we're well on the journey for that. So that's kind of, for a completely new bespoke piece of software or a big new feature, that's more what you're looking at. But for bug fixes, then, yeah, they'll be for them to expect us to fix it for the next race, then they will have to explicitly say, this is what's gone wrong. For example, this squiggly line should be this squiggly line, and it's not, that kind of thing. So that helps us to reproduce it and understand the problem. But a lot of what we do is investigating when people say, this isn't working correctly, here's a screenshot with a circle around the bit that's wrong. Okay, well, where's that data come from? What systems does it pass through? Okay, now I've got the debugger set up and I'm stepping through all these different pieces of the chain, and now suddenly yes, I see now here, this is the bit where it diverts from where I'd expect it to, and that's the problem, and so on and so forth. That's the piece of configuration that was wrong, or that's the setting that's wrong, or that's the bit of code that's wrong, or whatever. So you do tend to find yourself diving deep into specific technical areas occasionally, and engineering areas, to be able to understand those issues so that you can turn them around. Okay, I think people keep wanting to come in, so if you do have any other questions, then please feel free to talk to me. As I said, we are looking for people to do a job very similar to what I've just described, so you'd be more than welcome to come and talk to me about that as well. But yes, thank you very much for coming, and hopefully see you around in the next few days. Thank you.